All right. Um, so in theoretical sense, the idea of DAG is not that hard. The idea of DAGs are very easy, but the problem with DAG is that if you are going to one subject area expert to draw a DAG, he will draw a DAG. If you go to another subject area expert to draw a DAG, that DAG might not be the same as the DAG that was proposed by the first subject area expert. And that creates a problem because if you are going to 10 different subject area experts and if you are getting 10 different DAGs, which DAG you are going to use, right? So even if hypothetically finding the solution of a DAG is very easy, you just have to go to the DAGity website. But in reality, when you are working with observational data and you are trying to use this kind of idea into identifying confounder or confounding for your own analysis, this may not be that easy, right? So the complete knowledge or the full knowledge of the DAG, what variable is causing what, say for example, your age variable is causing which other variables, or your pain medication variable is caused by which variable and is causing which other variables. So these are very difficult questions under a specific research area. Which variable is impacting which other variable, and DAG requires you to have that complete knowledge, which is almost always impossible. So I'm going to talk about a technique today where you do not need full knowledge. You only need the knowledge of some aspect of it. Before I start, I should mention that this is all of this that I'm describing here are described in this one paper. So this is the main paper for you for today's lecture, and everything that I discussed today, including some of the video materials, are very well described in this very nice paper. So I'm just going to use some of the examples that are shown in that paper. So this is more about identifying which variable is a confounder and which variable is not a confounder and things like that. So the first criteria is that that variable needs to be pre-treatment or pre-exposure. So if you are thinking of controlling for a variable L, that needs to be measured before the exposure. So in a general cohort study, it can happen that you have a exposure measurement or a time of treatment, and prior to that, you can have a measurement of some variable. And even after the treatment was given, there can be some other measurements, right? But what this particular criterion is asking, take the measurement that was taken before the treatment was given or the treatment was assigned. And this is the general formulation of what constitutes a confounder in a DAG framework. So if, say, for example, this chronic disease is your treatment and this mortality is your outcome, you are basically looking for a common cause of both treatment and outcome. And that will give you the idea of whether this is a confounder or not. But things can get problematic in a sense that sometimes you have a pre-treatment variable which is impacted by two other variables. So in the language of the DAG, this variable that is that you have here, L, is a effect variable from two other variables. So in that case, when you have a collider variable, and I describe it in detail in one of the videos about DAG, if you have a collider variable, do not adjust for that collider variable, right? But if you are simply using this pre-treatment criterion, just because this L variable was measured before your treatment variable, you would attempt to control for that variable. But according to this DAG, this would be something that would be problematic, right? So obviously this pre-treatment criterion is probably not the best criterion to use. All right, so the second criteria, because we have seen in one of the DAGs in the previous slide that pre-treatment criterion might not be sufficient. So the second criterion is try to figure out whether there is a common cause, right? So this is the general definition we follow for identifying confounder. So we not only try to find a variable that is pre-exposure, but we also try to find out whether that pre-exposure variable is also somehow associated with your outcome. And if we can find such a variable, we call that variable a common, uh, we say that that variable follows this common cause criterion. So it has to impact both. But in this DAG, as you can see, uh, you will have this L variable that is impacting your treatment, and this U variable that is impacting your Y, and that is impacting your L. So in a DAG terminology, whenever you have a U variable, that usually means that that variable is a unmeasured variable. So in this case, this U variable follows this criterion that U variable is impacting your A, because this is a open path, and this U variable is also impacting your Y, but U is unmeasured. So in that case, you cannot really adjust for it, right? So this is one of the restrictions of not having the variable that you can measure. So to accommodate that problem, there is this extension of common cause criterion, and the extension says that the variable does not have to be a common cause. It can be a child of a common cause. So U is a common cause for Y and A, but you can a child of U, or something that is affected by U, can also be included in the adjustment variables that we need to adjust as a confounder. Confounder is something that is distorting the relationship of your interest. So if you are basically interested about this treatment and this outcome, you are basically trying to figure out whether there is a variable that is distorting this relationship. That is the definition of a confounder, right? And if you think about it, that is a conceptual idea. That, I mean, in the measurement sense, how to translate that to measurement is a very different idea. So implementation of that idea is always coming with when you are dealing with your data. But this DAGs, how one variable is impacting with another variable, these should all come from a subject area expertise background, right? So I think I do understand the source of confusion, because in a statistics course, when we try to find out whether A and Y are related or not, so whenever we are dealing with a regression, say for example the regression could be like this, that uh, you have your Y, which is measured by or explained by X Z variable, right? And in a general sense, we are saying that Y is explained by X and Z. But in the statistical courses that you have taken, it never talks about when X was measured, when Z was measured, when Y was measured. That was not really something that is taught in the general statistics courses. So that is something different in the epidemiology context, because we need to understand when these were measured, because that is related to the causal interpretation that we are trying to make out of the beta coefficients that we will get out of this regression, right? So we are still using the same statistical models and ideas, but now we are operating under a very specific situation, because if it is certainly possible, if you get a non-zero beta coefficient here, it is certainly possible that you can also run a regression on X, on Y, and Z, right? And that will also give you some other coefficient which is also non-zero. But does that mean that the X variable which was measured before and Y variable that was measured, and Y variable that was measured afterwards, I'm still getting some significant alpha. Does that mean that this has causal interpretation? No. So that is the distinction between the conceptual idea that we are imposing on this epidemiologic study versus some of the things that we have already learned in the statistical courses. Of these three definitions are interconnected. So in here, I'm just requiring a variable to be measured before the treatment. In here, I'm requiring the variable to be associated with both. And in here, I'm saying that it can be a bit more complicated than that, where if this is not measured, I can take a variable that is caused by this variable, right? So we are building on the ideas to try to identify what better way we can try to identify confounders. All right. So now that we have this extended common cause criterion, even that has some problem, and that is because, say for example, when you have a situation like this, that say for example for this DAG, where L is causing your A, but L is not causing your Y directly, right? And in this scenario, generally speaking, without the extended causal common cause criterion, you would not really consider this L to be a confounder. So this disjunctive cause criterion, what it requires you to think about is not only take which variable is causing your Y, also take the variable that is causing your treatment as well. So that means that it does not have to be a common cause. So when you are talking about both, that is a common cause. But this criterion is more liberal in the sense that we are talking about not only the variables that impact your treatment, but we are also talking about the variables that are impacting your outcome. Do you see how that they are different? Because in the previous case, what we were interested in is that they have to be common cause. But in here, what we are saying that they do not have to be common cause. They can be only cause of treatment, and also they can be only cause of outcome. And according to this disjunctive cause criterion, we can adjust those variables in our regression model. Limitations of this disjunctive cause criteria, that it could accommodate some of the instrumental variables as well. And that concern is addressed in the modified disjunctive cause criteria. Let me try to draw something. So I have this A variable, right? And this Y variable. And I can have a U variable that is impacting my L variable, and that L variable is impacting this. And this U variable could be like this, or I could have this U variable impacting my A, and this U variable is impacting my L, and this L variable is impacting my Y, right? So this is the criterion 3, the extended common cause. In your disjunctive criteria, you do not need these variable. You just need a variable that is impacting your L. impacting your A, or a variable that is impacting your Y. You do not need to conceptualize a variable that is a common cause. So one of the concern about this disjunctive cause criterion was that if you have an instrumental variable like this, then you would adjust for this variable in your model as well. But we already know that if you are adjusting for instrumental variable in your regression model, when your modeling purpose is causal, then it is going to introduce bias in your analysis, or at least make your variance estimates poor, right? So in the modified criteria, there are two parts. So this is a modified version of the disjunctive cause criteria, and it says that avoid adjusting for any known instruments, right? So generally speaking, if you have an instrumental variable, if it is known that this is acting as an instrumental variable between the relationship between A and Y, then adjust for it. Otherwise, do not worry too much, right? So this is only part one of this modified criteria. There is another part that says that if you have a variable that is unmeasured, but this is a common cause, then try to find a variable that is a good proxy of that unmeasured variable. So when I include the not including instrument part and include the adding proxy variables in the disjunctive cause criterion, I am getting my modified disjunctive cause criterion. For the modified disjunctive cause criterion, there is one limitation that if you adjust for your mediator, that will split into the total effect into direct effect and indirect effect. And when your aim is to find the total effect of A on your Y, that is something that will not give you the correct estimate of your total effect. And that is something that I have already explained in the lab C. If you look at that lab C, that will give you a much better understanding of what happens if you are adjusting for a mediator. All right. So when we are talking about mediator, one of the things that is very important is to establish the temporality. Are you familiar with Bradford-Hill criterion? I think whoever is interested in causal inference, that should be the first thing they should read, because it gives you how many, 7 or 9 criterion. And one of those criterion is establishing temporality. And this is very important because you need to know whether your exposure was happening before your outcome or after your outcome. If your exposure was happening after your outcome, then you are probably doing something called reverse causality, because you are trying to interpret something, but in reality that happened in reverse. And this temporality is also very important when you are trying to do any kind of mediator analysis. Say, for example, if I am trying to do a mediation analysis from a cross-sectional study, right? What is the main concern the reviewer would have is that all of the things that I'm saying, that this Y is causing my M and M is causing my A and things like that, I cannot prove that from a observational study or cross-sectional study in particular, where everything was measured at the single time point. If I was dealing with a cohort study where treatment was measured and then M was measured, the mediator was measured, and then the outcome was measured, then it is really possible to do that kind of mediation analysis. So understanding the temporality is very important. Even if you are dealing with a cross-sectional study, you can try to have an assumption, and sometimes you might have some ways to verify that assumption, whether some variable was measured or happening before the other variable. If there are some additional questions that were asked in the questionnaire about the timing of that event happening. So that is a very special scenario, but in general, establishing temporality is very hard from a cross-sectional study.